We're going to start learning a few applications of definite integrals over the next couple of weeks. And our first one is going to be thinking about definite integrals as net change. And this is just an application of the fundamental theorem of calculus, actually. So let's remember one way to write the fundamental theorem of calculus was that if I'm taking if I'm integrating a derivative, then I take the antiderivative, which is just going to be the original function f, I plug in b, and then I plug in a. And so let's interpret what this means. So this piece here is a rate of change of the function f. Because remember, derivatives tell us slopes of tangent lines or rates of change. And then what we're doing over here is we're taking the original function and we're subtracting this. So this is the net change in f as x goes from a to b. And this might not make a ton of sense right now, but let's skip to the first example and then we'll go back to their net change theorem. So if we are integrating the rate at which water flows from a tank. So let's let f of t be v prime of t because it's a rate at which water flows. So it's going to be the volume changing. So this example doesn't actually ask a question. So let me ask the question here. So what does the integral from a to b, well, let's just put numbers on here. The integral from 2 to 10 of v prime of t dt tell me? Well, if we use the fundamental theorem of calculus, this would be v of 10 minus v of 2. Remember, v prime is the rate at which water is flowing into the tank. So this is 10 gallons per minute or something like that. V is the volume at time 10. And v of 2 is the volume at time 2. So if I subtract the volume at time 10 from the volume at time 2 from the volume at time 10, this is telling me how much the volume has changed. T equals 2 to t equals 10. So that's telling us how much additional water went into the tank in those 8 units of time. So this is the net change theorem. The net change theorem tells us if I take the integral of a rate of change, it tells us the net change. Okay, and this always just makes more sense once we start applying it to problems. So if we look at this one, this is the rate at which people enter an auditorium for a rock concert. We've got the function here. And so again, this is a rate. That's crucial to notice that this is a rate. And this is measured in peoples per hour. Initially, there's nobody in the auditorium. And then the doors close when the concert begins. So in order to figure out how many people entered the concert or how many people are in the auditorium, we would want to integrate that rate from 0 to 2. Because if we integrate the rate, that will tell us the number of people at time 2 minus the number of people at time 0. This will tell us how many people entered the auditorium in those 2 hours. Okay, the calculation of the integral here is not really the most important part for us, but we can anti-differentiate this. So we're going to get 1380 t cubed over 3 minus 575 over 4 t to the 4th. We'll plug in 0 and 2. When you do that, you should get 980 people. So notice that we're integrating a function that is people per hour. And we're getting people out as our units. Okay, so let's just keep going. So we've got an intersection. We know that cars turn left at this rate of cars per hour. We want to know the total number of cars that turned left from 0 to 18. So to get the total number that turns left, we're going to integrate this function because we're integrating a rate of change. And so that will tell us a total number of things. So we have 60 root t sine squared t over 3 dt. This does not look like a function that I want to anti-differentiate. If you try u substitution here, it is not going to work nicely. And this is not just a simple function that we can anti-differentiate. So I'm going to show you how we can integrate things like this on our calculator. Sometimes we're going to get integrals that are not nice to do by hand, and we'll need a calculator to do them. If you don't have a TI-83 or a TI-84, you should let me know, and we can talk about how to handle these problems otherwise. So let me show you how to do this on a TI-84. So this is just my emulator here. So the way that you do this is you press the math button, and then you're going to go down to the Fn int. That's our integral. So number 9. And then if you have a TI-84, your calculator is going to have everything set up really nicely for you. If you have an 83, I can tell you in class how to deal with that. So we're going to put in our bound 0 to 18. Our function, what had t's in it, our calculator just uses a variable x. The x lives here, so just use x. Don't worry about the fact that it's a different variable. And so then to put in the sine squared, I'm going to put in sine of the x over 3, and then I'm going to square that whole thing. So I put that double set of parentheses to show that I'm squaring this whole expression. And then I put the x here to tell them that x is the variable I used. And if I press enter, this will give us our answer. The problem asked us to round to the nearest whole number because we're dealing with cars. So I would say it was 1,658 cars went through this intersection. Okay, so let's jump back in to thinking about velocity now. So velocity problems are crucial problems where we see net change, especially in a physics class. And so what happens here is, what happens if I integrate velocity? What does that tell us? So we remember that velocity is the derivative of position. So I can replace this integral with s prime of t, where we think of s being the position function. The antiderivative of s or s prime will just be s. So we're going to get s of b minus s of a. So this is the position at time b minus the position at time a. This is a change in position. This is just telling us how far away I am from where I started. This is usually called displacement. Displacement tells us how far we are from where we started. So what could happen is a particle could move forward and backward and forward and backward and end here. This answer here, displacement, is just telling us the distance from where it started to where it's ended. It didn't tell us how far we moved total. It just tells us how far are we from where we started. So if we want to know the total distance, we have to think about integrating an absolute value of a velocity function. And so what happens here is that if we think, like, if this is our velocity function from A to B, when I integrate, that stuff is positive. This stuff is positive in the integral, and then this stuff becomes negative. And that's why this original answer tells us displacement, because anything where I'm moving backwards gets counted negatively. In order to get the total distance, I need that blue part to be counted as a positive value because I traveled a positive distance just in the negative direction. So we have to integrate the absolute value of velocity. That might seem hard to do, but I'll show you how to do that in an example. Okay, so if we look at this example here, if we're looking at the displacement, all we need is the integral of velocity. So in this case, this is t squared minus 4. That's when we can anti-differentiate 1/3 t cubed minus 4t from 0 to 3. Plug in 3 and subtract what you get when you plug in 0, and you get -3. Our units here are going to be meters. So this tells me I'm -3 units away from where I started. Okay. Now, if we think about distance traveled, let's look at the graph of this function. So this function looks like that. The vertex should be on the, y-axis. And it's going to cross the x-axis at -2 and 2. So this is our velocity function. So we're going from 0 to 3. So we're looking for this. In order to get the distance traveled, we need this area to be counted positively. So we're going to look at the integral from 0 to 2 of my velocity function. And I'm going to make that answer positive because right now it's going to be a negative number. And then I'm going to look at the integral from 2 to 3. That's going to give us this area of my velocity function. I can put absolute values around that, but we know that's already going to be a positive number. When you calculate this whole thing, I got 16/3. I got negative 16/3 out from the integral, and we put absolute values. This piece here gave me -3 plus 16/3. And when we add that all together, we get 23/3 meters. Okay, so the difference between displacement and distance is a little bit strange, but if you have questions about that, ask me in class.